All right, so the notes are just in regular places on the lecture site, so please check. And the tutorial from last Friday, all right, so the materials are already there. Let me just show you very quickly, just in case you missed that or you want to review them, okay? So just for your information, the tutorial videos, the tutorial materials are also part of the study materials. So you gotta make sure, so for the later test, they will cover the tutorial materials. So make sure you keep up with the space. Okay, so you can see under the lecture site, you'll see tutorials, week number 2. Right, so I'll put up the material for week number 3 this week as well. Okay, do that a little bit later. Okay, so let's see. So far in the tutorial, we basically were just reviewing about 2D arrays. And you definitely want to make sure how to do that in Java. I think the exercises that we have done so far should be good enough for you to get started. So I think later on, once we get to adjacency matrices for implementing graph, that should give you a little bit more comfort about implementing this stuff, right? So that's why I want to get you to brush up the details about 2D arrays earlier. And we did some big O as well, simple ones, but I want to go over with you 2 examples that's going to be a little bit more sophisticated about big O. Especially the later one is going to be calculating the so-called average running time for one of the dynamic array strategy. I want to go over that too with you, okay? But before that, I want to just do some little bit more review about the big O, and then if time permits, we can go over some property as well. If not, we can do it Wednesday. Okay, we'll see. All right, quick recap from last time. All right, so from lecture last Wednesday, right? Let's see what we covered very quickly. Quite a bit of pages, but the concept there is just different things. So we basically finish off the discussion about decide by contracts, about client-supplier, benefits versus obligation, and also pre-state and also post-state, right? So lots of terminology there, so make sure you go over the materials and make sure you get the ideas, right? And then we talk about partial correctness versus total correctness. The only difference is about whether or not you can assume termination. So every time if you got recursion or maybe iterations like a loops in your algorithm, you have to worry about termination. So that's something we'll have to cover as well later on when we talk about other algorithms. And you want to, precondition and postcondition, right? So if you actually got an abstract data type, ADT, you want to make sure every operation there should really have some predefined and well-specified precondition and postcondition, okay? Of course, one way to implement precondition in Java is you can say if the input does not satisfy a certain condition, let's say the array is not sorted for binary search, in that case, you might throw some exception, right? And we talk about modularity, in different contexts. But the main keywords for you to notice will be about individual modules and also interface specification about how you can compose them together. And the final product will just be an assembly of the modules. And each module should be also reusable. So the same kind of idea can be applied to different contexts. Doesn't need to be software. Could be sometimes hardware or maybe integration of both. So about some real life example there, also modularity and also hardware strictly, and also this will be like a PLC, programmable logic controller, just some industrial example about how you can use modularity, right? Very common principle to implement. And the reason that we are mentioning about this idea about modularity in 3101 is because you don't want to think about individual algorithm you're designing or implementing should be treated in isolation. They are actually put into practice in certain units, like a module. So your algorithm might just be an individual, let's say individual operation right here, but you also want to see the bigger context about how the algorithm is being used in module and also in the assembly of modules, right? So that's why the bigger context also counts for your understanding. All right, and then ADT, right? Just remember we got a list of operation and also precondition, postcondition for each operation. And Java classes are kind of like an approximation of the abstract data types if the precondition and postcondition are clear to you. But sometimes it may not be the case. No perfection in reality. All right, okay, that's about modularity, design by contracts, and also ADT, right? It's a nice little lecture, to really give you the broader context about how the algorithm can be used, not just in isolation, but in a more integrated context. Right, and then we move on to reviewing asymptotic analysis, right? So the slides there, I may not cover every slide because many of them are actually covered also in 2101. So I would say you definitely want to review them. They might be covered in a future test because we still got to use asymptotic upper bound in this course as well. So I'll just review some important facts and possibly property as well. But today, I just want to go over some examples with you. I think that's more important, right? Just so you know how to solve problems, especially the second one. So we talk about when you want to calculate asymptotic upper bound, notice the running time function, which you normally have to derive from some given algorithm, f of n. It could be something like this, with some multiplicative constant and with some lower term, things like that. And then you got some reference function for which you want to prove that the running time function is a big O family member in that, right? So that's the visualization we kind of showed to you last time. So you can review the intuition that we spoke about. And this is the more formal definition. Whenever you're given f of n, you want to prove that f of n is actually a member of the big family of the g of n, right? You got to find two things. Number one, you want to find the multiplicative constant. Number two, you want to find the starting point for the input size where you're going to get the upper bound effects, right? That's something we also try to look at in the tutorial session last Friday. You can go over some example there. So any example that we didn't do from last Friday, I'll also give you some solution. Actually, you can already find a solution on the slides. They're kind of adapted from the slides. I picked one of them, the more challenging one, the last one, and we can do it together today in the class first. And then we'll do even more challenging one later. All right? Guys, any question about the basic definition here for big O? We good? Yes.
A squiggly function, it would be under and then over and then under and then over.
Yeah, I would say if you're typically, well, at least also for this course, the running time function you're going to derive for your algorithm most likely is going to be quite regular. There should be a pattern for you to follow. It's not going to be like a suddenly up, down, up, down, up, down. So it should be quite easy for you to actually find what's the bound for that. Mathematically, yes. If you really got some very unique function there that somehow got very unpredictable. But you can still apply this definition here to find the C and also the N0. It could be that your function might just be exponential. That's the only way to bound it. It could be, right? But I think that this one is purely mathematical, right, to see the definition. But as we get to more like a coding, like an algorithm implementation, normally you wouldn't get something very peculiar because the code you can write is very pretty much fixed syntax. Yeah. Good. All right, I'll leave the formal definition to you, but we do have some quick exercise to kind of rewrite this definition. Well, using predicate logic. We can do that very quickly as a little exercise because predicate logic is also something we might see a little bit later when we want to specify, for example, looping variants. Because looping variant is a very important concept as well to cover, but we do that a little bit later in the course. Okay. All right, so that's a visualization of one particular example, right? You want to see really the running time function, reference function. Running time function here. That's a reference function, and that's the reference function applied with the multiplicative constant. That's where you can see some upper bound effects starting from a certain point. Okay, it's going to be always the case where you want to prove something about big O. Okay, if no further question, I want to start with little exercise right here. Okay, that's a tutorial stuff. And right here. Right, so that's the mathematical definition we did last time. And this is the visualization. And now we just somehow want to use logical operators like a negation, conjunction, disjunction, implication, for all, and exist, right? So these are the stuff you learned from 1090. Or 1019, right? Whatever course that will cover discrete math, right? How do we somehow rewrite the definition for big O, right? So for this one here, I'll give you the answer directly. However, I do have some question for you to actually think about, right? Because the logical operator you're using here matters, okay? Let me just show to you first. So what we really want to define is that f of n is order of big O of g of n. We want to make sure it's a member in the family. Okay, so let me start with that to say f of n is a member of the big O of G of n. Right? So if you want to visualize that very quickly, it's like this. This is the family, big O of G of n. And you want to say that f of n is simply one member inside. So what do you have to show in order to prove it, right? So this will be the case if and only if, right? That's what you learn in the discrete math course. Because we always need to find two things, the multiplicative constant and also the starting point of upper bound effects. So these two are something you have to find by yourself. So there should exist values like this that you're going to find. So that's why we got to use existential quantification first. Okay? So we say that there exists the C and also N0. Okay? Of course, if you want to be more precise, you can say C here is a real constant. You can say C is a member of real number. Right? So Z is actually it's a set of real numbers, right? And also you can say that the N0 over here is a set of integers. So C is the set of what we can even say natural number. So you can think about natural number is the set that start with 0, 1, 2, etc. Because input size doesn't make sense to be negative, right? So we say natural number. And whenever we want to refer to a natural number in this course, it does start with 0. I know in some contexts, natural number may only start with 1, but for our context, always start with 0, okay? Which makes sense. Input can be empty, right? Okay, so once we got this, these two dummy variables set up, we're going to say the following, okay? And we're going to say this. It is the case. So what's going to be the property for C and also N0? So you can say something like maybe C should be strictly larger than 0. You can say that corresponds to this. And also the N0 is larger than or equal to 1, which corresponds to this definition here, right? So all the necessary ingredients that we saw in this definition here should somehow appear over here. It's just a different way to express, right, the constraint, all right? And this. And then this part over here, we have to use some nested quantification because somehow we want to express starting from N0. Starting from N0 over here, the upper bound effects simply occurs for every N value, the input size, that's actually larger than or equal to N0. That's something we will want to see. And for this part here, we're going to say for every one of them, right? It's going to be universal. Okay? So this part here is going to be some universal quantification that we're going to write out. All right? And for this universal quantification, let's see what we should write. So here we're going to say for every N, so you can think about the N here is input size. Okay. And then you can say here, let's say N larger than or equal to N0. So we start at exactly N0, including N0 itself. That's the starting point for the upper bound effects. So here comes some very important stuff here, all right? So and then we got implies. Oh, by the way, so whenever we say this here, that means logical implication. And that is something I also want you to think about, but I'll make it more clear. Let me just finish that definition. I'll give you some mental exercise to try, okay? So we're saying N should be larger than or equal to N0. And then if this is the case, and then the consequence should be for the N here, the upper bound effect should be the case, right? So what I can write is, so right here, okay, I just don't have space, but this should be the consequence part for the implication. So that'll be the f of n should be less than or equal to C times G of n. So think about this one here is the upper bound effects for us. Now, what we want to really see, let me just say one more thing, and then I'll give you the exercise to try, to think about. You can also say the n here, of course. You can think about n here, n should be maybe a natural number, right? Because it should be an input size, it should not be negative. Okay? Now, here's a question. Okay, I'll put it the next page. Okay, that's a question you want to think about. Why are we putting here implication as opposed to conjunction? Okay, I'll give you a little bit of hints right here. You can see that over here, we're using implication here. I'm asking, would it be right if we say conjunction over here? All right, that's the question. And the way to think about it is more like this, okay? The hints. You want to somehow consider the truth table of these two, right? Why don't we work them out, right? It's also like a prerequisite for this course. Okay, let's now work it out, all right? Because P and Q, let's say in general, if you got P a proposition and also Q also proposition, P can be true or false, Q and can also be true or false, right? So we got true, 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 false, false, true, false, false. And then we actually got P and Q. And also we got P implies Q. All right? This one should be rather easy. The only way you can make it true is when both of them are true. If either of the operand is actually false, you get false. This one is easy, okay? All right? How about this one here? What should be the entries for implication? Go ahead.
True, false, true, true.
Yeah, that's good. So the only way to really make this implication false is when the antecedent is actually true, but the consequence is false. All right, that's the only way. Okay, I wouldn't dive too much into it, but that's something you can review, or you can come to me. I can explain further for you. So the only way to make it false is right here. Other than that, if both of them are actually true, implication would be just true. There are also two cases where the implication here would be true trivially, when you actually got the antecedent here being false. When the antecedent is simply false, it doesn't really matter what the consequence is. It would just be true. All right? That's basically the hints. So here is your exercise. Okay? You want to consider an sorry, let me just get rid of this page. That shouldn't be there. I want you to look at this predicate over here, especially this part, right? The right way to use it should be implication. However, if I replace this implication over here just by conjunction, why would it not be appropriate? So the way to really justify it is to really consider the truth table and see how they differ and find out the case to explain why that case would not actually be consistent with the formula we have over here. All right? So that's an exercise for you. All right? Think about it. Okay? But I already gave you the hints. The real hints is really to compare the truth table between the two operations, the logical operators. And once you find out a particular edge case where they're different, you will see that why using implication here is the way to go, but not conjunction. All right? That's exercise for you. All right? Good. Any questions just about what we are reviewing here? Okay. And of course, if you want to speak about why, the truth table for implication goes like this. Maybe that's something you don't quite understand from the previous math course. You can reach out to me. I can also explain to you. But we maybe wouldn't spend the time in the class. Okay, that's one. Okay, that's good. And then let me just, I think I do have some background over here, but I'll rather solve the problem with you right away today. Just let me go over one more background, and then we'll solve the problem. Okay, we got 2 problems to solve. Especially latter one is going to take us a good, big chunk of time for today. So let's dive directly into it. Let me go over one more thing. Okay, this diagram here you also see on the slides. So these are the typical running time functions you will see, right? So you want to make sure your running time should really be growing as slowly as possible over the input size being increased, right? So that's really something you want to review, okay? So the rate of growth, the slower, the more efficient. The slower or flatter. The slower relative to input size increase. The more efficient. So these are the typical running times you will see even for the graph algorithm. Like the kind of peculiar functions that Josh just said might be in theory, but we may not run into them. Right, good. Just stay a little bit more practical here. All right, so that's a diagram you want to go over. Just make sure you know. For example, you can see the best way to have is a completely flat. So that will be the constant running time. That means your algorithm runs just the same. Doesn't matter how large the input is. It stays just flat. On the other hand, you really don't want to have exponential. But we do have some algorithm there, in which case it's just not polynomial. In which case, the only way you can solve it will be brute force. That might be something we'll see a little bit later in the course. Right? But these are the typical ones. Okay? Just make sure you review about the different growth and make sure it's clear to you. Okay? All right, let's now try to solve the problem. Right? There are 2 exercises I want to go over. Let's go over the first one here. Okay, but to really go over that one, I want to review 2 mathematical properties before we go over that one. So one is about calculating the size of some integer interval, right? So that's something we want to review. So let's say here, let's say calculating the size of integer intervals. Okay. So the way to express that would be AB. I think this will be consistent notation with what you did in maybe in the calculus class, right? So when you got square bracket over here, it simply means closed interval, right? That means including A and B. So this one here simply means closed n. That means the n value is included. So you can think about this one here. It's really to talk about A plus 1, A plus 2, all the way to B. And we're asking how many numbers are there in the interval. So this will be very important, especially when we actually have a loop. We want to see how many iterations we have, which is going to impact the running time. Okay? Okay, so the question is, how many numbers do we have in this interval, right? Just notice that we got A and B included. Okay? And the formula, if you want to know, will be the size will just be B minus A plus 1. If you're only trying to approximate the running time, plus 1 without plus 1 wouldn't really impact the final answer. But when I really want you to derive the running time, I do want to see that you calculate as precise as possible. So I think the plus 1 here is important, right? Let's just see one example here, right? You can plug it in, right? So how many numbers are there? For example, between, so example here. And by the way, A and B here can be negative as well, as long as they're continuous, okay? So here we have, let's say, from 34 all the way to 100. So we're asking how many numbers are there between 34 and 100, including 34 and 100, right? So the size is going to be 100 minus 34 and then plus 1, okay? So 67, right? You can verify, okay? Yeah. But of course, you can try like a smaller interval just to convince yourself. This one I just want to show it to you, right? So and sometimes you may not have exactly the same, exactly like a concrete number here. You might have some maybe variable like a x or y, or even just n or n minus 1. So you want to make sure you calculate precisely. So that's why the formula here will be important, okay? Oh, another one I can definitely show you. These are my notes, okay? So for example, if you think about, let's say in the context of array, if I know that my array has indices 0 all the way to, let's say, x. So you can think about this is the minimum index. And the x over here is the maximum index. So now I want to know what's going to be the size of the array, right? And we know pretty well the maximum size of the array should be the size minus 1, right? That's something we know pretty well. So we know the size over here should be the array size. Should be just x minus 0 plus 1, which will be just x plus 1, which makes sense, right? If you got the maximum index being 9, the array length should be 10. Right? So just another way to verify the formula. Right? Pretty simple formula, but it's going to be very useful for us. Right? Closed interval. That's number 1 I want to review. Number 2, which is about arithmetic sequence sum. Right? I'm pretty sure you learned that maybe back in 2101, but it's really important to brush up. Right? There's another one, which is to calculate the sum of geometrical sequence. That's something we'll do maybe a little bit later once we encounter that example, but not just yet. Okay, we'll do that when we really need it. Okay, let's say, for example, if I have, let's say, the typical example. If I say I have 1 plus 2 plus 3 plus 4 plus all the way to 100. Right? It's arithmetic sum, arithmetic sequence, because we know that between each number you got some fixed constant. So plus 1, and also plus 1. And how many terms do we have in total? 100, right? I kind of chose that so it's easy to see. You got 100 terms. Okay, the formula goes like this. I'll generalize it just in one moment. Okay, so the formula will be, you want to basically do the following. The beginning plus the end. Beginning plus the end. Multiplied by the number of terms. In this case, it would be 100. Divided by 2. All right, that's the formula. In case you're kind of wondering why, it will be calculated in this way, right? Just informally. If you look at that, 1 plus 100, 101. 2 plus 99, also 101. 3 plus 98, also 101. And the number of 101 we have is exactly 100 divided by 2. We got 50, like 50 pairs. That's kind of the intuition, right? But you don't need to prove this, in the test. But this one here, I just want to show to you. I think to really figure out the geometrical sequence sum will be a little more interesting. But for this one here, I just want to give you some intuition. Okay? So let me generalize it. Okay? Because here we're just make it simple, right? Like a plus 1, and also the number of terms for you to see is quite easy. But we do want to observe some general pattern, especially for the second example we're going to see today, right? So let's see this. So in general, the sequence will look like this. You got I, which we said is the start term. And then I plus, and then I plus over here, another fixed constant. So the C here is what we call the common difference. a common difference. And then we say plus, the third term would be I plus 2 times C. Okay? So you can think about this one here is the first term in the sequence. So this one here is the first term. And this one here is the second term. And this one here is the third term. Okay? And etc. Right? Now, here a question for you, right? So let's say the pattern will go on like this. So let's now figure out the last term. I plus some number here times C. All right? So let's make some assumption here. Okay? Let's say the following. If I tell you that we have n turns in total, let's say, in that case, what should I fill out right here? Should it be n? N minus 1, right? Because you can see that here, for the very first term, it will be as if I said I plus 0 times C. So 0 here is exactly 1 minus 1. And here I got 1 times C. 1 here is 2 minus 1. So here I got 2 here, which is 3 minus 1. So now if I got n term, so now if I got nth term, so what should be this multiplicative constant here? It should be n minus 1. Right? It's a very important insight into the formula because we'll see something like this very nicely when we talk about one of the dynamic array strategies. Okay? So here it would be n minus 1. Okay? So that'll be the arithmetic sequence. And what should be the sum? The sum will be like this. It's going to be beginning term I plus the end term. I plus n minus 1 times C, right? So, okay, let me make it, just highlight it quickly for you. I here, and, oh, okay. So, n term and n term, right? Multiplied by the number of terms, which we assume to be n. And then the whole thing divided by 2. Okay? This one here. So what should you know from this formula here? 2 things. Number 1, you want to make sure you really understand about how the pattern is evolving right here, especially why this should be n minus 1. That's how you actually see the inside of the term, how it actually progresses, right? That's number 1. Number 2, the way to remember the formula is not to just remember the symbols over here, okay? Just remember it's going to be the first term plus the last term multiplied by the number of terms divided by 2. Okay, I'll write it down. What you got to remember is this. It's going to be the first term plus last term multiplied by the number of terms divided by 2. So that's all you have to somehow, put in quote, memorize. Oh, maybe yellow would be better. There we go. Okay. Yeah, again, remember this formula here generally. And then for the last term, you want to make sure you know how to see the pattern. Right? So these are the 2 things you want to keep in mind for this formula. Okay? And we also got to pay attention to similar details when we talk about geometrical progression. Okay? We'll see later. Okay? Oh, and then this one here, of course, you can try to simplify it. And then this one here, you can feel free to do it, but I'll just give you the simplification. Right? C times n squared plus 2I minus C times n divided by 2. But you don't need to memorize that, right? Don't do that, okay? But the conclusion is, we know that this one here is big O of n squared because this is the highest term. So we know that this is big O of n squared. So this one tells us whenever you got the running time being somehow formulated as a arithmetic progression, it's going to be n squared. Okay, that's kind of the intuition you want to have. Okay, that's something we also see, right? Big O of n squared. Okay. Any questions about this? Okay, good. Why don't we just do one exercise over here, and then we'll take a short break. Okay, let's do the first one. I think for the second one, it's going to take us definitely about the second half of the course. Sorry, the class, not course. Okay. All right, let's do this one here. Okay. You may have seen something similar maybe back in 2101, but that's okay. I just want to do it, just make sure we kind of review about how to use the arithmetic sequence sum, and also see how we can observe the pattern for the for loop, right? I'll let you guys maybe take a look at this code here very quickly, right? Maybe back in 2101, you kind of had to calculate the number of primitive operations. But in this course, we don't need to. We don't need to calculate a precise one. But you ought to have some approximation of the primitive operation. Just remember, every primitive operation will take constant amount of time. Okay? So each primitive operation takes big O of 1 time. That is something we assume, okay? We don't need to calculate a precise number. But to see what's really primitive operation, please take a look at the review slides, right? That's something I don't need to go over the bullet point with you. That's something you can review. All right, just take a look at this one here, just for 1 minute. I would say even before deriving the asymptotic upper bound, you can even take a guess about what the complexity is for running time here. And I can tell you that the critical thing we want to make sure we get right and precise is in line number 4, j is assigned to I, right? That's really the part we want to get right. If we simply say j is assigned to 0, then the whole thing is going to be much easier, okay? But it's j equals I. Okay, just take one more moment, just at least you get familiar with the code here. And a triangular sum, the method name here, somehow give you a little bit idea about how we're going to do it. Okay. So let's say this is in the test or exam. Part 1, what's the asymptotic upper bound? That's something you can always maybe take a guess first. And then in part 2, you will try to show your work to justify it. So part 1, what's the asymptotic upper bound? Anyone? N squared, okay? Agree? Okay. I would say this one here, more or less you can see we got nested loop. But of course, having a double nested loop doesn't always mean you're going to have a n squared. Not necessarily. Depends on how the bounds are going to be going to show up at the runtime. That's something we're going to see. Okay. But this one here is rather straightforward, but we do have to care about the details because it's not exactly starting from 0, but from the current value of the outer loop counter, right? So that's something we have to look at that, right? We want to look at that more carefully. Okay, but it's not too bad. Okay, let's now talk about this one. So turns out it's going to be big O of n squared. Yes, part 1. But we're going to show precisely how. So the way to understand this one here, first of all, let's start with something outside the loop. You can see that this line here is just variable assignments. That one there just big O of 1, constant. Okay? We don't really have to worry about, you may have to do some variable assignment, accessing some expression, might be separate primitive operation. We don't have to. Just put 1. Whenever you think that's primitive operation or number of primitive operation, that's constant, right? Just add up to be constant. And then we can see that this return outside the loop is also 1. All right? That's also good. Okay? And the body of the loop right here, this one here. Again, you don't need to calculate the precise number of primitive operations. You can just see that we're basically just doing some array indexing, which is constant, and also we're doing some arithmetic, like a plus arithmetic, also basic, and also variable assignment, also basic, just some small number of basic operations. So this one here is also 1. All right? So these are the constant part. What we need to figure out is the pattern for I and j, which I'm going to make it a little bit thicker. This part here. Oh, too much. That should be good. All right, this part here. Because we know for every, well, I'm going to show to you, for every combination of I and j, you can see I is the loop counter for the outer loop, j is a counter for the inner loop. For every combination of I and j, we have to execute line number 5 once. Okay, I'll write on the inside. Okay. Each combination of I and j corresponds to an execution of line number 5, which is right here. And line number 5 itself is really just constant. So we just got to work out exactly how many combinations are there between I and j. Right? Okay, that's a very important something you want to know, you kind of understand, right? So let's now look at the patterns for I and j. Okay? So we're going to work out the patterns of I and j together. We start with I, because there's an outer loop. We know I can actually go from 0 all the way to n minus 1, right? Because n minus 1 will be the last iteration value, because when I is equal to n, it's going to make the less than false, so you don't even get to execute that iteration, right? Okay, good. So let's now map it out. So let me change the color a little bit right here. Okay, so let me use blue. Okay, I here. So I know that it's actually 0, 1, 2, all the way to n minus 1, right? From the outside outer loop point of view, for this header over here, I know that I is going to be from 0 all the way to n minus 1. And we can apply the interval that we just learned, well, we just reviewed. How many outer loop iterations do we have, right? It's basically, so the number of iterations for the outer loop is going to be the size of the interval from 0 to n minus 1, right? So from 0 to n minus 1, inclusive. That one will just be n, right? n minus 1 minus 0 plus 1, okay? Awesome, okay? This will be useful. I'll show you why, okay? And just remember, this is something we just calculated, okay, right here, okay? And let's talk about in the loop as well. Because for every value of I, we also need to execute the in the loop, right? That's exactly the meaning for the nested loop. So now when I is equal to 0, we know that j is going to start from the value of I, right? So for this particular I value, the j value is going to start from 0, right? From 0 all the way to, again, n minus 1, right? So let's talk about j value. Okay, and then I'll pause a bit, just in case you want me to clarify any parts. So when I is equal to 0, j should be starting from I, 0 here, and then plus plus, right? 0, 1, 2, all the way to n minus 1. Are we okay with this? All right, good. And then, what about when I is equal to 1? In that way, j, again, is going to start with 1, right? So it's going to be from 1 and then 2 all the way to n minus 1. And then when I is equal to 2, it's going to be from 2 and then n minus 1. Okay? And if you keep going, how about this one here? The last one. N minus 1, just itself, right? Just 1. Good. Okay, you can see the pattern here. It's very important to calculate the pattern. Okay, let's try to interpret this table here because I think usually your fellow student may have some confusion here. Okay, let's say I just look at just 2. How do I interpret this particular entry, right? You can think about this entry here is referring to a particular combination. Combination of the ij being 0 and 2. Okay, you can think about 0, 0, 0, 1, 0, 2, all the way to 0 and minus 1, right? Different combination. Each combination is going to trigger one execution of line number 5. All right? All right. Now, let's now work out. We're almost there. Question for you. Let's say just for this particular row, how many executions are there for line number 5? How do we calculate? Go ahead.
You find the
Number in the interval, right? What's the interval? Tell me the interval, please.
from 0 to n minus 1.
Absolutely. From 0 to n minus 1. And this one here will be from 1 to n minus 1. Which will be n minus 1. So this will be from 2 to n minus 1. All right, just in case you're wondering, so that'll be n minus 1 minus 2 plus 1. Okay, so that will be n minus 2, right? And keep going. And this one here, you can think about it's really from n minus 1 to n minus 1. Okay. And you'll be no surprise if you apply the formula, it's going to give you 1. Okay. For this row here, it corresponds to n executions of line number 5. N minus 1 executions of line number 5. How many executions in total? Add them up. Okay. So now the number of execution of line number 5. Okay, you can see the sequence here. We got n minus 1, n minus 2, all the way to 1. Isn't that a arithmetic progression, right? That one there is simply going to be n plus n minus 1 plus n minus 2 plus all the way to 1. All right, remember the formula? Beginning plus the end multiplied by number of terms divided by 2, right? It's going to be something divided by 2, right? Beginning plus the end. How many terms do we have? From n all the way down to 1. N terms, right? All right, we got n all the way to 1. That's something you can also calculate, which will be, you can think about this one here. You can definitely calculate a precise answer, or you can simply say it is big O of n squared. However, be careful. So when we say it's big O of n squared, we're only talking about, okay, this part here. So what we have worked out is this part here corresponds to this part. But to be complete, we still got to add up this one here. Of course, it wouldn't impact the answer, but conceptually we should. Okay. So finally, we can say the running time is the big O of, you can do some intermediate work here, basically 1 plus n squared and plus 1. Okay, let's just be precise here. So you can think about the one here is really corresponding to line number 2. And the one here is corresponding to line number 6. And this one here is really corresponding to the nested loop, which is from 3 to 5. And of course, it will still be the same, big O of n squared. But just for completeness, you ought to really consider other lower term. But you, of course, you can drop them, right, eventually. So that's the final answer. Okay, the reason that it's called triangular is if you look at the patterns for I and J combination, you can see that nicely it's a triangle right here. Okay. So I would say anytime you're actually facing some loop counter with some peculiar pattern for between I and J, or sometimes I and J and K, you ought to really draw a table to really for you to see the pattern. Once you work out a pattern, you may have to formulate the iterations using some sequence. Could be arithmetic, sometimes it could be geometric. It depends. Okay? So I think in this example here, just one example for how you can figure out the pattern and then derive the writing time. Right? Any questions? All right, so this will be the easier one for today. We're going to do a harder one. All right? Awesome. Well, hopefully that can make you comfortable at least. Why don't we take a very short break, and then we'll do dynamic array afterwards. Get your iClicker ready, please. Okay, so let's now do the second exercise on the big O. Okay, this one here is going to be 2 parts. So we want to talk about a concept called dynamic array. So I will just go over some context with you. So this technique for dynamic array can be applied to either implementing a stack or implementing a queue. I'll show you some Java code about without dynamic array, what's going to be the situation. And then to really implement the dynamic array, there will be 2 strategies, as we briefly mentioned in the beginning of the course. One is called fixed constant. The other one is called doubling. So today in the class, I want to do most of the fixed constant just to at least I can give you all the information you will need. We'll see if we can finish derivation today. If we cannot, we'll definitely finish that on Wednesday. But the second part is about how to figure out the running time for doubling. That's something we can leave to the tutorial to really solve that again together with you. Okay, so we'll see how that goes. Let's now just go over some slides. It'll be slide number 29 on your lecture slides. Okay. So when you actually want to implement the stack and queue, that's something you did maybe back in 2101. So you can use an array. And of course, in any programming language, whenever you want to create an array object, you have to give a size, concrete size. It has to be maybe 100, 1,000, or 2,000. The thing is, doesn't matter how large the initial size is. At some point, in theory, you might still have to fill out all the slots of the array, and the array is full, right? So now what do you typically do? Maybe in 1021 and 1021, 2030, or even 2101. What we said is if you really fill out the array to be completely full, in that case, if you try to add one more element into the array, you might just throw some exception to say maybe the queue is already full, or maybe the stack is already full. That's all good. But we really want to create something different. Okay? Let's think about, let's just go over the slide quickly, and I'll show you some modified code. Let's now take a quick look at this fragment here, right? So you can see that we actually try to implement a stack, right? The stack ADT, right? Last in, first out. So we have some maximum capacity, let's say 1,000, right? It's not very big, but at least we can store up to 1,000 elements in the stack. The problem is, as soon as we have filled out the stack completely with 1,000 element, let's say after 1,000 pushes. So now if we want to add a 1,001st element, we're going to trigger something called precondition violation, right? We're going to say if the current size of the stack is exactly 1,000, and then we don't allow the clients of the stack to call the push anymore. So in some way, it's kind of inconvenient for the clients. So they should be aware about what's the maximum capacity of the stack, right? In this case, 1,000, right? So the idea about dynamic array is we want to relax this particular constraint or precondition, right? We want to relax that constraint to say the clients can really add as many elements into the stack as they wish. They're only constrained by the actual computer memory, which is pretty much limited. Which is pretty much unbounded, right? You can definitely add a lot of stuff to the computer memory. So I'll visualize this in just one moment just to show you the really fundamental difference between the two strategies. So that's one thing, and also for the Q as well, right? So you can see when the maximum capacity is reached, we also throw some precondition violation, all right? So let's now just visualize what's going on, and then I'll get to this one here, okay? Okay, so you can think about, we got two things here. So we are really talking about implementing a stack or a queue, some container, okay? So what we learned before is using an array of fixed size. Some fixed capacity. Okay, let's say capacity is simply just C. Or maybe let me say max. So let's take the stack for example, right? So let's say once I create a stack object, I can say stack s dot push some element here, and then I can say s dot push some element here, and I can keep doing it. Let's say up to now, I got one push, second push, all the way to, if I got max pushes, if the max happen to be 1,000, this will be 1,000 pushes. If this happen to be 10,000, this will be 10,000, right? So now, if I try one more push, this is going to trigger some precondition violation or exception, right? So this one over here will be max plus 1 push. And this one here is going to be a precondition violation. You know, for example, you may have something called maybe stack full exception, right? Okay, like that. And similarly for the queue as well, depending on how many in-queue operations you can call. So what we're doing now is something called dynamic array approach. Using a dynamic array. With adapting capacity. Adapting in the sense that we're going to modify the size of the array as we go. That's something I'll show to you. It's very easy to program, just some conditional. But we're going to learn about the running time. Okay? So what does it really mean for dynamic? Dynamic in the sense that we're going to grow the size of the array when necessary. When necessary. And there's something you will see later, but the insight is you don't have to grow the size of the array for every push, for example. Only every once in a while, you have to somehow grow the size of the array. So the frequency of growing the array is going to determine how efficient the algorithm is. Okay, I'm going to write the insight right away, and that's something you will have to also try to convince yourself once we work out all the math, right, for both approaches. So there are two strategies over here. 2.1 is something with a constant increment. That's what you will see on the slides. And 2.2 is something called doubling. And to really determine which one is more efficient intuitively, you want to think about whichever that's going to require the dynamic growth of the size less often is going to be more efficient. The one that demands less frequent resizing is asymptotically more efficient. More efficient. Right, that's an insight. I'm just kind of give you the conclusion right away, but we're going to see exactly how that can be reflected in the math. That's something we'll see. Okay. Okay. So we talk about less frequent and more efficient. Okay. So how does dynamic array really look like? So basically, you can just say push, push, push all the way indefinitely. Okay. So this one here, you can think about, you can just say push and push. You never have to worry about any like a stack full exception. Okay, that's really the advantage about using dynamic array. No worry about the stack being full. Of course, in a very extreme case, if you're adding so many elements that's kind of already reached the capacity of your computer memory, of course, you can still get like a crash, but it's a different issue, right? So, but in theory, we are really trying to use a dynamic array, so the clients of the stack, they don't have to worry about, at some point, they have to stop pushing in the stack. They don't have to worry about it in the dynamic array. Okay, we got about 12 minutes or so. I would suggest the following. I will go over the code about the first strategy here with you. And then I will do some visualization. And then that should take about 10 minutes or so. That should be until the end of today. And then I'll give you a little bit hints about how you're supposed to work out the running time. That's something I would like you to try before Wednesday. And it's not going to be a surprise. What we're going to see is you got to use arithmetic sequence sum at some point in the running time derivation. Give it a try, and then on Wednesday we can start with that, okay? Because after this, I would like to start maybe covering some maybe AVL tree, just about tree rotation. But for the doubling strategy, that's something we can do in the tutorial, just to solve some extra problem together with you, okay? Let's see, right? So I want you to just focus on the code right here, all right? I'll guide you to read the code, right? It's actually very logical, but you got to watch out the details, okay? So we still have a class called array stack. So we're implementing a stack using an array, okay? And then we got actually 3 integers here. We got capital I, capital C, and also capacity, right? Let's see what they really mean, okay? So the I here is the initial capacity of the array, of the stack. Initial capacity. Okay? And then the C here is this. Every time if the current capacity is already full, is already reached to its maximum, C will be the number of elements we want to free up to really, let me write it down first, okay? The extra space to allocates when full. For example, let's say C here is 5. What does that mean? Let's say my initial size of the stack is the array is 10. After I've got 10 elements inside, I'll resize the array to be size 15. After 15 is already full, I resized into 20, etc. Right? So from 10, 15, 20, 25, and 30. So every time when the current array is full, I'm only going to add 5 more spaces into the array. So I can push another 5 times. That's really the constant increments it's trying to say. Okay? But I'll visualize that in just one moment. Okay? And the capacity over here is just about the current maximum capacity. The current limits you can think about. Okay? So these are the critical variables that you will actually have to look at when you study the code and also the derivation. And we simply got an array over here. That's the array we're going to use to really implement a stack. Okay? And then we got some constructor over here. So let's say initial size is simply 1,000. It got to be some number. Let's say 1,000. And the capacity is 500. That means every time when we actually, when the array gets full, we're going to add 500 slots into the array. So given these, what does that mean? Dynamically, the array sizes is going to be like this. In the beginning, we got 1,000 slots in the array. Let's say all the 1,000 got full. We're going to increase the size of the array by 500. So you become 1,500. Let's say this one gets full again. What will be the next size? 2,000, and etc. Just keep going, right? Dynamically, the code is actually going to do the magic. It's always going to somehow run some loop, which I'll show to you. That's really going to be the bottleneck for the running time. But it's going to be 1,500, and then 2,000, and etc. And of course, once you get a capacity initially, so you're just going to create the array. And then we just set the, well, T here is just like a pointer, just about where we are in the last element, right? It's more like an implementation detail. So at this level, maybe I will let you trace the code to convince yourself, right? That's something I can leave to you. All right, so just notice about I and C and also capacity, right, in the constructor. All right, let's now take even closer about the push. Don't lose the big picture. Once this dynamic array is implemented, we want to make sure we can call the push for as many times as we like without ever running into the precondition violation. So when you study the slides, you will see that right before this version here, without the dynamic array, we will say something like, when the size, current size is exactly equal to the capacity, that means we're full. In the previous version, without the dynamic array, we're going to throw that exception. But now we don't do that, right? Now, in this case, what do we do? Okay, let me just write down annotation for you. Okay, so this one is saying, when the current array is full, when the array is full, increase its size by C. And remember, C is one of the variables we have, right? That's what we're going to do. And if you look at here, what's going to be the running time, though? Right? We have basic, well, let's think about what's, let's see what's happening here. Let's say this. If currently I have this, so the current maximum is capacity. And I know that the array is completely full. All the stuff, are stored in the array, right? How am I supposed to create another array? Well, think about, let's say this is data. Right? What I want to have is, I still want to have this data reference over here, but it is going to point to a bigger array. And the array is actually going to be capacity plus C. So this part here is going to be capacity. And this part here is going to be the new space I'm going to create for future, like a further pushes, right? This will be C. And I want to copy over everything that's already here into over here. I got to do some copy, right? So the next push will start from here. Okay, so this will be just copy. So you can think about this part here is about copy the existing contents in there. And then the very first slot after at here, okay, so this will be where another push is going to come from, okay? This is going to be the first new push. Okay. So how do we do exactly, right? You can see that this part over here is really about copying the entire array into this part of the new array. That's what the for loop is doing, right? Just copy index by index, from index 0 to index 0, index 1 to index 1, and etc., all the way to here. And notice that this new array over here has the capacity plus C, right? That's a bigger array. And eventually we want to make sure this new array temp is actually going to be the data, right? Data is assigned to temp. So we basically think about this one here. Okay, I'll draw a little bit better. So what we have is, this is the temp, which is bigger. And once we have done the copying, we're going to say data, rather than pointing to here, is going to point to this array over here, right? That's a new data to be used onwards. So also before Wednesday, try to also look at this coding over here about how the dynamic array is going to work. But is there any question about coding I can answer quickly? Yeah.
Is the reason why you made I a final variable just because you wanted to?
So I here, I just want to make sure there's an initial size you want to have. The initial size doesn't need to be C. It can be any number. So I'm kind of separating between initial size, which can be some number, and every time when the current array gets full, how many more spaces do you want to create? That's another.
Yeah, but did you just make an I to make sure all the numbers have a variable attached to them? So you didn't just write 1,000 equals.
Yeah, there's got to be some number, right, to start with. All right. All right, guys, I got about 3 minutes. Okay, so now I want to give you enough hints, and you guys try to see if you can work out the running time. Okay. Let's say this. What we want to work out is, let's say I got n pushes. Okay? Do as much as you can before Wednesday. Of course, I'll go over with you about the solution. It's a little bit sophisticated, but I want you to give it a try. Okay? Assume that we got n pushes in total. N can be arbitrarily large. Okay? Can be way beyond the current capacity, right? So I want you to look at this diagram here. We have some initial size of the array. Okay? So green simply means we got some free space. So initially we got I elements for us to fill out, fill out the array. Okay? And we keep pushing. Let's say after I pushes, okay? So that means this part here is completely full. And then we are going to execute this part to grow the size of the array, right? So we're going to copy over everything here. So we've got to copy all the things into here. And then we're going to create this extra space for C, right? And then let's say we got another C pushes. So that one there is going to fill out this part here. And then we have to copy everything over, and then we actually have to create some extra space for C, right? And so on. Okay? What I want you to think about, let me just also help you work a little bit here. For this particular resizing, how much work do we have to do? It's really about copying over all the existing contents from initial, right? From this, let's say this is really completely filled out. We want to copy everything over into here, right? How many copy do we have? How many iterations do we need in here? I, good, okay, good sign, okay. This one here, from here to here, we know that the work is I. How about here? I plus C, awesome. Follow that pattern there and see if you can figure out some arithmetic sequence, and that should lead you to somewhere. Okay? Give a try on this here. I think it's very important on Wednesday before the class. At least go over the slides part, only about a few slides, to see the difference between dynamic array versus non-dynamic array. And look at the code, make sure you understand the logic, and try to see if you can formulate the running time from there, the derivation. And I'll go over the details with you also on Wednesday. Okay? Thank you so much. I'll see you later.